And today we'll be discussing ArcGIS spatial analytics tools and techniques. Unfortunately, there will be not enough time in the 30 minutes to summarize model selection information. Therefore, today we will not be discussing how certain models are selected. That being said, we will be discussing the tools you use or can use to develop your criteria for model selection. Let's first start off with a high-level overview of spatial analysis and data science, the root of what we will be discussing today. In the limited time we have on this topic, I will provide a high-level overview of spatial analysis and harnessing Esri tools to complete analytical workflows. At the heart of Esri, we are a GIS company with GIS users, developers, and spatial data consumers. My goal of this presentation and overall mission is to provide users with the tools needed to become a data scientist in your everyday work through leveraging the strengths in your GIS capability. You have a leg up on the competition because of the breadth and knowledge surrounding GIS, and now that GIS just needs to be applied to data science techniques. On this slide, you see a couple different polygons with information. First off, we have data engineering. This relates to curating data sets and preparing them for analysis. We will dive into this topic and show some of the tools associated with data engineering and how it can be completed as a task. Spatial analysis refers to modeling data with a spatial component and is the bread and butter of understanding how objects are related in space and time. Data analytics coupled with spatial analysis provides powerful insights into your results and location information. Big data analytics is something we won't touch upon heavily during this presentation, but it is an important topic for taking large data sets and understanding that you can distill them down into meaningful information. With distributed computing processes and allocation of resources, big data is becoming more accessible in your everyday work. Machine learning is another topic we will lightly touch on. Over the past few years, it has gained a lot of traction and popularity in predictive analytics. It is important to note that a lot of topics encompassing machine learning and artificial intelligence have been around for decades. The problem of the deployment and use was constrained by computing resources. With Moore's law on processing power and chip size, we've achieved success in implementing machine learning and AI models with our current resources and libraries that are available, which we will run through a bit within this presentation. Modeling and scripting is another topic we will delve into today to better understand how you can harness spatial libraries and statistical analysis with R or Python within the Esri environment. And finally, we have visualization, exploration, and sharing data. We have to ask, how will we represent our results in a meaningful way to a large audience without exposing the complexity of our problem? Spatial visualization provides a representation of insights derived from our model. Lastly, sharing our model results. With the advent of topics such as Kubernetes and containerization, sharing models and reproducing them with different data has become very seamless and not a large overburden on the workflow or the time frame of the workflow. So why spatial analytics? What are we attempting to achieve or derive insights from? Now, that is a loaded question. What is on this slide is a mere snapshot of what can be done with spatial analysis techniques. We could solve site selection problems where the user would like to determine optimal sites from COVID-19 testing facilities to retail store locations, financial institution ATM and banking locations, and quick service restaurant site selection, like determining where to place a new McDonald's to have it be economically successful and generating a lot of revenue. And this can be achieved through analyzing attractive markets by determining store performance, the demographic landscape, and competition, all which have a spatial component. The key understanding here is that these analyses contain a spatial component, a location or dispersion across a geography. whether it be block group level or zip code demographic information, all the way to address locations for, let's say, restaurants. In the case of COVID-19 testing site selection, we can evaluate vulnerable populations and communities with limited access to health services, while also understanding accessibility of, for instance, the population coverage of pharmacies within a 10-minute drive time. We can also solve routing problems to determine optimal paths for multiple delivery sites. Beyond that, we can determine maximum capacity delivered. What's the maximum capacity of a truckload and how much is being delivered at each location? We can determine the hours of operation, how long are shifts, when do they end, and multiple fleets. How many trucks exist within one fleet or many fleets to ensure that all the real world variables are at play in our model. With territory design, we can build balanced regions across a specific geography under specific constraints. For example, let's say you have multiple accountants serving the Northeast region. Each accountant can be assigned certain accounts in the region so that all accountants are managing roughly the same revenue. If they are spread out, they can be covering their immediate region so that there's no more than a 4-hour drive time from their home. The top 3 bullet points can act as business decision support systems for spatial analysis and complicated problems. But we can also use spatial analysis to develop environmental modeling, such as identifying critical source areas of pollutant emissions from non-point source pollution modeling. Think phosphorus emissions on agricultural fields. We can also look at the spread of invasive species and predict in certain environments if that invasive species will thrive based on the relationships between the environment and where existing invasive species exist. So what sort of utilities are we going to discuss today to conduct our spatial analysis? There are a myriad of tool sets within Esri suite for spatial analysis in both the user interface and scripting capabilities. There are multiple platforms to produce analytical models and work with spatial data. Today, we'll delve into ArcGIS Pro and look at both the geoprocessing tools, but also take a glimpse into ArcGIS R-Bridge and Python for use in ArcGIS Pro. And I just also wanted to highlight that there are user interfaces for ArcGIS Insights, ArcGIS Online, Enterprise Portal, and we'll focus on just Pro and then scripting capabilities and ArcGIS notebooks where you can develop your scripts and run them within ArcGIS Pro. Now, for accessing most of these tools that will be described, you will have to have a spatial analyst license or a network analyst extension. Now, let's get into what it takes to approach and build a spatial analytics model. I would say that around 70%, if not more, of the actual work in data analytics and modeling is consumed by data preparation. This goes back to the notion of garbage in, garbage out. If you feed the model poorly curated data, your results will suffer and reflect that input data. First bullet point is cleaning data. Users need to clean data to assure that they can run a specific analysis that meets the correct input data criteria. You should try and either remove or fill in any null values, whether that be you completely remove the row or summarize an average for that attribute field and place that average value in the missing null. Another cleaning data purpose is to encode categorical data. So think of a book genre as a categorical data. This should be encoded with unique values. Next is normalizing or standardizing data. It's taking values from different fields that you would like to relate, but are completely out of range from one another to make them in range and relatable. This can also be described as feature scaling, where you fit the data. Pivot tables can summarize larger data sets into a more condensed form. Aggregating data is the act of bucketing data into specific fields or within a geography, rolling up the data. And finally, we have feature extraction. This is the act of reducing the number of features in a large data set while still being able to summarize the bulk of the information. And this is widely used in machine learning. And I just like this image on this slide here. This is actually a model builder workflow for selected COVID-19 testing sites that I've recently built out. And Within the red box is the entire data pre-processing steps. So this is quite a significant amount of the workflow. So it's imperative that you really get the data pre-processing down so that your analysis produces results that can be, well defined for insights. Next, we have data engineering in ArcGIS Pro. What sort of analysis can you explore in ArcGIS Pro? And the short answer is there's a ton of analysis. It can be overwhelming at times, but we'll try to break it down into different categories for different types of data. And first, we'll start with and mainly focus on spatial statistics tools. When we talk about regression analysis, we're talking about continuous data sets such as temperature, rainfall, elevation, or demographics. And within demographics, I'm talking about age, income, etc. This is measurable data. When we talk about classification analysis, we're talking about categorical data, job type, car type, again, demographics, but we're talking about, for instance, race, gender, marital status. So models used for both regression analysis can be used for classification analysis. It just depends on what type of data you're working with, whether it's categorical or continuous. Another analysis that is probably familiar to a lot of users is the term spatial autocorrelation. How can you describe this term? Well, it's associated with spatial variation and spatial stationarity. It attempts to determine if objects are clustered, dispersed, or random within geographic regions. For instance, if you're determining critical source areas of high phosphorus concentration within an agricultural field, how do you quantify the p-values within that area? P as in actually phosphorus. You can relate known measurements in specific soil horizons and the known chemistry of the soil to determine their relationship and estimate phosphorus concentrations based off of the known values and the soil horizon relationship. We can also assume P measurements near to one another have similar concentrations because of where they're located. And the values will degrade as the distance increases from that known location. Geographically weighted regression refers to the extension of ordinary least squares regression model, where it not only fits the appropriate regression line on a scatter plot, but also supports features within a specific geographic region. A way of thinking about or describing GWR, geographic weighted regression, is through Tobler's law of geography and also spatial non-stationarity. First off, all objects are related to one another. However, objects nearer to one another are more related than objects farther apart. But also, how are certain variables affect a value you're studying in a region over time? Geographically weighted regression attempts to determine the spatial relationship between a dependent and selected independent variables within a defined neighborhood. Essentially, with this analysis, you can attempt to determine how, for example, manure is related to increased phosphorus concentration released from critical source areas a day after that manure was dispersed on the agricultural fields and during a period of intense rainfall. So you can analyze a time frame or a snapshot of the environmental conditions and look at how intense rainfall changes the concentration of phosphorus from critical source areas over time. Finally, we have machine learning techniques. And like I said, I won't go deep into this because of the breadth of theory and information on this topic. However, I would like to mention some exploratory techniques such as decision tree, random forest ensemble, and density-based clustering. These analysis, bar density-based clustering, can be used for both regression and classification models. A basic workflow would be to pre-process your data, train them in a specific model with a subset of your data, and then test it on the remaining subset of data you did not use to train the model. Decision tree is based on the information entropy theory and essentially splits data into sections based on their values. The algorithm selects the splits and gives an average value for each split section. If a random point is placed within any of those split sections, then it's determined to be associated with the average value in the given split section and subsequently classified. Random forest is an ensemble of decision tree models. Ergo, the user determines how many decision trees to calculate. The more trees you add in the model, the more accurate your results, but also the more computing resources you will need for the analysis. Using image segmentation, feature extraction, feature selection, and classification, random forests can be used to determine land cover types using remote sensing satellite imagery. The topic of object-based image analysis showcases the use of random forests in action. Density-based clustering determines the amount of clusters to be developed to form a set of data based on the proximity of each location. The tool is used to cluster and classify new points. Next, we have spatial relationships, which help us to describe the characteristics and associations between different types of data. Pattern analysis can support the notion of objects related to one another in specific regions and help to identify areas such as the relationship with having a high volume of a particular crime and 911 calls. Collocation analysis measures patterns within a local geography and determines spatial associations between two categories of points, such as the relationship between ATM use and its proximity to convenience stores. Spatial relationships can also be used to predict areas where grocery stores have a higher foot traffic and are better performing. For instance, two raster layers representing the kernel density estimator for showcasing two different variables is present on this slide. We have the left image providing insights into the distribution of grocery store locations in a specific region, and the right image represents kernel density estimator for population within the same geographic region as the grocery stores. We can use these two layers to evaluate the spatial variation in population density in grocery stores across a geographic region, and possibly estimate store performance based on the population density and the grouping of grocery stores. Finally, interpolation methods such as inverse distance weighted and kriging can help to estimate values with two or more points, between two or more points, creating a continuous surface of estimated and known values. For instance, if you have the known locations of weather stations logging temperature, then you can use inverse distance weighted to estimate the temperature values between all the stations within the study area to have a continuous surface. Now we're going to get into the utilities and tools you can wrangle in ArcGIS Pro environment to conduct exploratory data analysis. So we've gone through our data pre-processing, and we're understanding how spatial statistics can be leveraged to determine continuous and categorical data. And now we're going to actually explore that data with exploration techniques. So first off, we have to understand what exploratory data analysis is. It is relatively self-explanatory. It's just when an analyst determines important variables and gets a better understanding as to what type of analysis may need to be conducted to answer the necessary questions of the problem. It's an iterative task. You might come to a result and realize it is completely off the mark. Therefore, you go back to exploring your data to get a better understanding for what you are working with. So how do we conduct our EDA, or exploratory data analysis, in ArcGIS Pro? Well, we have a few options. We can leverage the spatial stats, geoanalytics, or geostatistical tools in the geoprocessing pane. We can initiate ArcGIS R-Bridge that will allow us to access R packages and develop R scripts from basic to advanced spatial statistic analysis, something that we will get into in the next slide. We can work with and develop Python scripts in ArcGIS Pro. On top of that, we can clone Python virtual environment in ArcGIS Pro. And this is another topic we will familiarize with later on in the presentation. Finally, we can build our scripts in different interfaces such as ArcGIS Notebook or Jupyter Notebook. ArcGIS Notebook allows the user to develop and run code snippets within ArcGIS Pro. This is a similar environment to Jupyter Notebooks. If you have Jupyter Notebooks files, then you can open them in ArcGIS Pro and run your code snippets. And this image on the right-hand side is actually demonstrating an ArcGIS Notebook with a basic random forest classification. It's importing packages, the data set, and it's also splitting the data into training and testing. And all of that can be edited within the ArcGIS notebook. So the ArcGIS R-Bridge. First off, we're going to understand its capability, and it's a very powerful tool with a lot of resources online to help you get started. The ArcGIS R-Bridge allows users to tether R stats packages to be used on spatial data within the ArcGIS Pro environment. Using ArcGIS R binding, the user can leverage their ArcGIS Pro data within R. You can enrich your data within R and then, for instance, run a k-nearest neighbor algorithm to determine how your data might be clustered and predict information. You can use the ArcGIS binding function in library in Jupyter Notebook, RStudio, or within your notebook in ArcGIS Pro. All you need to do is have R installed and initiate it in the geoprocessing window under options in ArcGIS Pro. So this is showcasing the options window, which is accessible through the ArcGIS Pro project tab. You select geoprocessing, scroll down and find ArcGIS support, R-ArcGIS support. Click on the folder and point that location to your R application. This is an example of R being used with ArcGIS binding in Jupyter. First, in the cell 1, we install and initiate our packages. In this instance, we're installing the R-GDAL package, and we're calling the library ArcGIS binding so that we can tether our geodatabase and make a connection with ArcGIS Pro, which is what the second cell is doing. It's checking that we have a connection with ArcGIS Pro, and it's pointing to our geodatabase. Finally, we can define the environments, the environmental variables, and for instance, build out a roster file. And that's being conducted in cell 3. And we can take this R Jupyter file, and we can actually open it up in ArcGIS notebooks and edit our script and run our script within ArcGIS Pro. Next, we have Python, and specifically the Python 3 build used with ArcGIS Pro. And I'm sure a lot of you in attendance are familiar with ArcPy. And before this capability of cloning environments in ArcGIS Pro was available, analysts would have to create their own virtual environments via command line or work within the ArcPy environment that came standard with either ArcGIS Desktop or ArcGIS Pro installation. If the user does not create a virtual environment or did not create one, they would run the risk of library dependency issues where some installs are not compatible with others and their system would become an unorganized environment with no versioning control. With managing your Python environment in the ArcGIS Pro project tab, you would select the Python window and you'd have this Python package manager pop up where you could manage your environments, clone them, and install packages for certain cloned environments. For instance, in the Manage Environments window, we have the ArcGIS Pro Python 3 environment. If we were to clone this in our project, select the radio button for that cloned object. We could install specific packages that are only used within the ArcGIS Pro project that we're working within. And we can toggle between different ones that we can update, install, or add different packages. So we can explore different statistical packages. And there's a wealth of information on these packages and how they can be leveraged for certain types of analysis. So within these project environments, we can establish specific packages and dependencies based on what type of analysis that environment will be used for. Then we have Python exploratory data analysis in ArcGIS notebooks. And I think this is really just good to highlight the idea that we could build geospatial analysis models with ArcPy tools that also exist within the geoprocessing toolbox. You can have geoanalytics tools, geostatistical tools, spatial statistical tools. We can also run scikit-learn and develop machine learning models like random forest. We could build out linear, multilinear, and nonlinear regression analysis in Python. We can build and calculate raster data sets and determine values such as the normalized difference vegetation index, or run an analysis like we saw with the kernel density estimator on grocery store locations and population. We can also develop network analysis and modeling with, for instance, back to the site selection, we can develop a location allocation model model in Python under ArcGIS Pro notebook so that we can actually design our entire layer environment of the location allocation model in this script to enter the correct input data and then run the analysis. This is as long as they have the dependencies and libraries available within their environment. And finally, we have results visualization. How can we visualize the results that we just produced? Well, for business analytics and community analytics, we can actually use infographics to summarize geographies and specific information we're interested with. So if you have business analyst or community analyst, you can actually create infographics that summarize data. ArcGIS Pro, we can develop or generate graphs for our spatial analysis. So we can look at different relationships between variables and how the data is distributed. We can also, and if you're familiar with ArcGIS Insights, we can port our data into ArcGIS Insights and develop cards to visualize specific information. Dashboards is another fine way to distill your results into meaningful visualizations. This is looking at, once again, a location allocation model dashboard. So I understand that this is a lot to unpack. There's a lot of information and it's difficult to determine where to start. You know, we only had about 30 minutes to really cover a lot of this material. But I'd just like to let you know that there are a lot of resources on Esri, especially for spatial analysis and statistical modeling. And if this interests you, I would highly recommend visiting e-learning platform and start looking at some of the e-learning plans curated for spatial analysis topics. There is even a machine learning lesson to get you familiar with the topic and how to conduct a random forest classification on spatial data. These are very powerful tools that can deliver powerful insights towards GIS and spatial analysis. And finally, I would like to direct everyone to our Esri Boston Hub page, where you can get information on events, news, and information about the Boston Regional Office. You can follow the hub to get notifications and updates on local events in and around Boston.